Alright, gonna do a quick small tutorial on Lewis dot structures. This will be uploaded on our text, but there's also another video on our text that would be probably important to watch as well. This is just kind of how I think of it, but by all means, look for more resources. Okay, so the first thing to remember when I think about Lewis dot structures is how many bonds things want to have. All right, for instance, oxygen wants to have 2 bonds, nitrogen wants to have 3, carbon wants to have 4. Now, when I say wants, I'm thinking of course, the octet rule. What everybody really wants is to be surrounded by 8 electrons. Now, for oxygen, for instance, oxygen has 6 valence electrons. If it had 2 bonds, like it does here, 1 and 2, now it has 8 electrons it's surrounded by. So it likes to form 2 bonds. That would also mean it has 2 lone pairs there, right, and 2 bonds. So if oxygen has a full octet and has 2 bonds, it doesn't have a charge. Now with nitrogen, it has 5 valence electrons. So that means it needs 3 more bonds to get to 8. So it has 1, 2, 3. So you can see a lone pair is 2, 4, 6, 8. Now with this 5 valence electrons, right? If it has 3 bonds, it's going to be neutral and not have a charge either, right? When it has a full octet, has 3 bonds, nitrogen has no charge. Now with carbon, same deal, 4 valence electrons. If it has 4 bonds, 1, 2, 3, 4, it has a full octet, it has no charge as well. Right, 4 valence electrons means it needs 4 bonds to get to 8. Now to analyze this a little further, take it a step further with now just looking at carbon. So carbon normally wants 4 bonds, so it has a full octet, 2, 4, 6, 8. If it has a full octet and has 4 bonds, it's neutral carbon. Right? Even here, 2, 4, 6, 8, neutral, neutral. Now, what if it has 2? We can zoom in a little bit here. So it looks more like we did in class. If I put 2 electrons here, right? So each bond has 2 electrons. So this carbon is surrounded by 2, 4, 6 electrons, not a full octet. So it has 3 bonds and not a full octet. When it has 3 bonds and doesn't have a full octet, we would say this oxygen has a plus charge. It has lost one of its valence electrons. Right? Each of these bonds is a covalent bond. So 1 electron, we'll make the red ones the oxygen one, or the carbon ones. So this carbon's missing one of its valence electrons, therefore it has a plus charge. So carbon with 3 bonds, not a full octet, plus charge. Now if you look a little farther over here, what if, right, again, same situation, the red electrons are from the carbon, the blue, we'll say, are from the hydrogen. It looks like here, this carbon has gotten an extra electron. Does it have a full octet? 2, 4, 6, 8. It does. But it only has 3 bonds, but has a full octet. Then it has a minus charge. Then it's a carbanion. 6 valence, 6 electrons surrounding it, 3 bonds, carbocation. Full octet, only 3 bonds. That must be a carbanion. Right? It's got an extra electron. There's a middle ground here, of course. A methyl radical. Now in this case, here's a carbon with 2, 4, 6, 7 electrons surrounding it, not a full octet, but has it lost any of its own valence electrons? No, you can see the red ones, 1, 2, 3, 4. So this has no charge, but it doesn't have a full octet, so it's not that happy. Now if you took a look at all of these as a whole, these are all pretty reactive species, right? Carbon doesn't want to have a negative charge. We talked about, or a positive charge, or not have a full octet. It wants to be right in the middle, right? So you can imagine the worst of these, if we were going to say one's the most reactive, what's the first rule of Lewis dot structures? That would be the octet rule. So which one of these doesn't have a full octet and is it hurting in the worst way? The carbocation, right? Because it's only surrounded by 2, 4, 6 electrons. Whereas the carbanion still has 2, 4, 6, 8. So it still has a full octet. It's still reactive, but it has a full octet. And then the radical is better off than the carbocation, but still not a full octet. Nitrogen, similar thing. Let's break that down. Nitrogen again has 5 valence electrons. So it has 1, 2, 3 there, and then the other 2, 5 there. And because it has 5 valence electrons, it wants to have 3 bonds to get to its octet. So 2, 4, 6, 8. Right? It doesn't matter where it's bonded. So it has 1 lone pair. Now imagine if this lone pair, let's zoom in, was red. What is going on if nitrogen all of a sudden has 4 bonds, such as an ammonium ion? Does it have a full octet? It does. 2 electrons in a bond, 2, 4, 6, 8. So it's happy. The first rule is octet rule. So it's happy. But the problem is, does nitrogen with a full octet, how many bonds does it normally or want to have? It normally wants to have 1, 2, 3. So if it has 4, something else must be going on. So if you look here, let's focus in on these 2 red electrons. They had to be right there. So nitrogen's donating both electrons for that bond. So it's actually losing some electrons. But again, we'll be careful here. Just because it has a plus charge, does that mean that nitrogen's electron deficient? No. So it's sharing them, these electrons, but is it doing it well? Absolutely not. Right? Nitrogen-hydrogen bond, the nitrogen's more electronegative. It's really still hogging the electrons, even though it has a plus formal charge. So how else does this look? Right, so right there. So it has 1, 2, 3. Those are its valence electrons. The other electrons are coming from, the blue ones are coming from the hydrogen. So here it has 2, 4, 6, 8. So it's a full octet, but it has 4 bonds. The nitrogen is going to have a formal plus charge, but the electron deficiency is all out here on the hydrogens. So what happens if we have a nitrogen with a full octet, 2, 4, 6, 8, but only 2 bonds? Then it has a negative charge. So a nitrogen with 2, 4, 6, 8, a full octet and 4 bonds is a plus charge. Nitrogen with a full octet and only 2 bonds is a negative charge because, again, it must have gotten an extra electron, right, that it didn't already have in its valence. So as you can see here, it has that extra red electron. That's why it has a negative charge now. All right, let's break down water, or oxygen, sorry, with water the same way. Again, oxygen has 6 valence electrons, so it needs 2 more bonds to get to 8. 2, 4, 6, 8. Oxygen with the full 8 electrons, full octet, usually wants 2 bonds. But what happens if it doesn't? What if it has 3 bonds? So here, hydronium has 2, 4, 6, 8. Full octet, first important rule. But it has 3 bonds, so that's similar to what going out with the nitrogen. If I go back and do this, some of these red, those electrons, that lone pair is now a part of that bond. So that oxygen is giving up electrons to make that bond. Again, though, who owns the electrons, oxygen or hydrogen? The oxygen really owns the electrons, even though the plus formal charge is here. Extending it again, what if oxygen has 2, 4, 6, 8, a full octet, but only 1 bond? That must mean it has a negative charge because it's, again, must have been given an extra electron that it's not using for bonding. All these red ones are there. Very similar across these things. So if oxygen doesn't form 2 bonds, it has to be charged. If a nitrogen doesn't form 3 bonds, it also has to be charged. If a carbon doesn't form 4 bonds, something else probably else is going on, either radical carbanion or carbocation. Simple stuff, halogens. Halogens want 1 bond because halogens have 3 lone pairs, right? 2, 4, 6. So they have 3 lone pairs, and they only need 1 bond to get to their full octet. So you can see a bromine-bromine bond. 2, 4, 6, 8, right? Hydrogen we've talked about a little bit. Hydrogen can lose an electron, become a proton, a hydrogen ion. It can gain an electron, become a hydride ion. It can exist as a hydrogen radical. And a bromine can exist just the same way. If it got an extra electron, it would be a minus charge, right? Because now it has an extra electron, so it would be negative. Or it could exist as a radical and have an unpaired electron with its normal 7 valence. All right, to summarize it, hydrogen wants to have 1 bond normally. Carbon with a full octet should normally have 4. Nitrogen has this 5 valence electrons, so it normally wants to, with a full octet, it normally wants to form 3 bonds and not be charged. Oxygen wants to form 2 with a full octet, it would not be charged. But there are situations where these will be different. We'll have a full octet and different numbers of bonds, and then the resulting carbon, nitrogen, oxygen would have a plus or minus charge, or maybe even be a radical. The halogens are easy. They only like to form one bond because they need one more electron to get to a full octet. So halogens have 3 lone pairs, oxygens have 2 lone pairs, nitrogen has 1. Always draw in your lone pairs. Great idea. Draw in those lone pairs. So how does this work in practice? Let's look at something like NO3. That should be a subscript, NO3 minus. So overall it has a negative charge and has an extra electron. There's a couple of ways you can do this. So the classic way, which is also written in our text, is you look at the elements you have and see how many valence electrons each of them has. So in this case, nitrogen has 5, oxygen has 6, but there's 3 of those, and there's 1 extra electron because we have a negative charge. So that adds up to, let's see, 6 times 4, 24 electrons. So we know we can't be done until we use 24 electrons. And of course, how many electrons are in a bond? 2. So we got to keep that in count. Now the other hard part is this: how do we start this? So usually the easiest thing to do is put the least electronegative element into the middle. So nitrogen versus oxygen, who's more electronegative? Oxygen is. So let's put nitrogen in the middle. And we have some ideas, right? We know nitrogen wants to have how many bonds normally? 3. So let's just go with that feeling. Nitrogen wants to have 3 bonds normally, so let's go with that. Now, let's start putting in lone pairs in the oxygens. The oxygens have their electronegative. Let's draw some lone pairs in on the oxygens. So this is a good start, but there's some problems here. We got to think about formal charges here for our individual elements. So let's count. Let's make sure we used 24 electrons. Let's count that up. So 2, 4, 6, 8, 2 electrons in every bond. 10, 12, 14, 16, 18, 20, 22, 24. We've used all of our electrons, so that's good. But let's think about formal charge here. Wait a second. Let's look at our central atom, this nitrogen. Does this nitrogen have a full octet around it? It does not. It only has 2, 4, 6. Well, that means if it only has 6, it must have what kind of charge? It's missing electrons then, right? It must have a plus charge. Something must be wrong here. It's missing electrons. Actually, I think it's missing 2 electrons, right? It might be even 2 plus. What about these oxygens? 2, 4, 6, 8. Well, that's good. How many bonds does oxygen have, though? Only has 1. At the full octet, we know that means it's a minus. So that means all these oxygens are also minus. So there's a lot of charge going on here, right? We got a nitrogen missing 2 electrons. We got 3 oxygens with negative charge. So maybe this isn't the best one, but it just makes sense here. So are we at -1? We have 2, we have 3 minus 1, -3, plus 2, that's still -1. So this is a valid Lewis dot structure. Now, is it a good Lewis dot structure? Let's maybe say no. We can make it a little bit better. How can we do that? What if instead of having we have a negative and a plus here next to each other, why not just make one of these lone pairs into a new bond, a new pi bond instead? And that would quench one of the charges and not make a 2 plus, that should be a trigger for bad. 2 plus should be bad. So what if we did So now I'm going to put one of those lone pairs into a pi bond. And now let's check our formal charges, see if we're okay. Again, I think this is going to be a -1, right? An oxygen with a full octet with 1 bond. An oxygen with a full octet with 1 bond is a negative. An oxygen with a full octet, 2, 4, 6, 8. 2 bonds, that's neutral, right? So that's nothing wrong with that. A nitrogen, though, with 1, 2, 3, 4, so now it has a full octet, right? 2, 4, 6, 8. Full octet, but it has 4 bonds, so that nitrogen should have a plus charge, right? So now we add up to make sure, did we get to -1 here? I think we did. -2 plus 1 is -1. Did we use 24 electrons? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Good. Biggest things here is this is tough, right? This 2 pluses kind of throws you for a loop. All of a sudden there's this nitrogen. We never saw a 2 plus yet. But if you see a negative charge next to a positive charge, you can usually make a new bond there, right? And bring those electrons there to make a new bond and get rid of one of those charges, both of those charges. Here is just the book kind of explanation. You can pause it here and take a look at this as well, right? They don't put the formal charges in right away, which I like to do to make sure it kind of makes sense to me to see that. This has an incomplete octet, which should always trigger you to say bad, right? Because the first rule of Lewis dot structures is the octet rule. Okay, so let's look at 3 different possible Lewis dot structures and go through the process with these. So the first one we're going to look at is CO3 2-. So again, thinking about before, what's the least electronegative element? It's carbon versus oxygen. So carbon is less electronegative. Let's put that in the center. And since we have 3 oxygens, let's start off just bonding the oxygens out there. But now we can look at this and say, well, wait a second. Like this is kind of your chemical intuitions should start to pick up here. We've been talking a lot about the octet rule, and you probably know something about from Gen Chem. Charges are bad at some level. If you can just start off by giving carbon 4 bonds, wouldn't that be a good idea? So let's just do that. And it doesn't matter which oxygen you pick. Let's just do that, right? Now we can always go back and say here, we'll add up valence electrons here. So carbon has 4, oxygen 6, 6, and 6, and then 2- is another 2. So again, that gets us to 24 electrons. So it's a good bookkeeping thing to make sure we don't lose electrons here. Now let's just start filling in lone pairs with what we have. So if an oxygen has 2 bonds, to have a full octet, it needs to have 2 lone pairs. If an oxygen only has 1 bond, to have a full octet, it needs to have 3 lone pairs. Same here. We don't need to do anything with the carbon because the carbon already has 4 bonds, and that should be a happy carbon and neutral. But if one of these oxygens, let's look at the formal charges of everything. So this oxygen has 2, 4, 6, 8, has a full octet, but only has 1 bond. So that means it must be a negative formal charge. Same with this oxygen. Carbon here has 2, 4, 6, 8, 4 bonds, full octet, it's fine. Another oxygen with 2, 4, 6, 8, full octet with 2 bonds, it is also fine. Do we use 24 electrons? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So that's a good check. Is our charge right? -1, -1. That's -2. Looks like we're good. All right, let's do the next one, NMe4+. So a lot of people don't know what Me means. Me means methyl, which is just a CH3 group. So again, here this is a little tricky though, because carbon and nitrogen, some people would say, well, carbon's there's less electronegative than nitrogen, so we should put carbon in the middle. And that's a little tricky. That rule doesn't always apply. So in this case, you kind of got to put nitrogen in the middle, actually, because CH3, a carbon can only have 1 more bond. It just doesn't work out. So let's put the nitrogen in the middle. CH3s, 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 CH3s. Now you could go through and do the whole adding up the electrons. I'm not going to do that because it's going to take too much time. You could do it and prove it to yourself. But as it stands right now, this carbon has 1, 2, 3, 4 bonds. So 2, 4, 6, 8, right? H3 means there's 3 more bonds there. Full octet, full octet, full octet, full octet. With 4 bonds, carbon is neutral then. So then must be nitrogen, but something's going on with nitrogen. Well, nitrogen has 2, 4, 6, 8. So it has a full octet, but it has 4 bonds. Nitrogen with full octet and 4 bonds means plus charge. So the plus charge is on the nitrogen. But again, don't forget your Lewis dot structures. The octet rule is the most important, but does that mean it's telling the whole story? If a nitrogen is bonded to a carbon, who owns the electrons? The nitrogen does more because it's more electronegative. Just because it has a plus charge doesn't mean that's where it's delta plus. So now let's get into the sulfur realm. And sulfur can be weird because sulfur is lower on the periodic table. And when you're lower on the periodic table, you can do something called an expanded octet. So we'll show you what that means in a second. But this should be a pretty familiar one from H2SO4. So HSO4 is the conjugate base of H2SO4, the strong acid. So here, again, we ask ourselves, what's our least electronegative thing? Some people will say, let's put hydrogen in the middle. But the problem with putting hydrogen in the middle, hydrogen only wants one bond. That's going to be weird. You can't really decorate around a hydrogen. So let's do a sulfur. Let's put sulfur in the middle. And why is sulfur in the middle? Because it's less electronegative than oxygen. It's actually lower on the periodic table, and that's one of those trends. So let's start putting the oxygens all around the sulfur. There's 4 oxygens. This makes sense. Let's put them all there. And one of these is going to have the hydrogen somewhere, probably on the oxygen, usually out there. We can add up the valence electrons if we want to at this point. So we could say each oxygen has 6, 6, 6, 6. Sulfur has 6. And then hydrogen has 1. Hydrogen has 1 plus the 1. Don't forget the 1. I almost did. The 1 from the negative charge. That would add up to something. What would that add up to? Math is tough sometimes. 2, 4, 6, 8. 32. There's a lot of electrons in this. All right. So start putting lone pairs in. Now I'm stopping here because I'm realizing something. Maybe you know this or not, but I can only have one negative charge, so I can't have these oxygens having negative charges. I'm not really it's not going to be a great idea to have sulfur with a bunch of plus charges. So the trick here is to recognize, well, wait a second, there's a lot of oxygen on sulfur. Sulfur is lower in the periodic table. Maybe it can have an expanded octet, meaning it can have more than 8 electrons surrounding it. Right? It's that third shell, so it can have more bonds. So I'm going to cheat a little bit. Right, and these are kind of things you can kind of just know. The sulfur is going to be willing to have 6 bonds. Okay? So that means these oxygens, though, are going to have 2 lone pairs each, which is going to make them happy because these oxygens then have 2, 4, 6, 8. Full octet, 2 bonds, neutral. 2, 4, 6, 8. Full octet, 2 bonds, neutral. Oxygen here, 2, 4, 6, 8. Full octet, 2 bonds. Different than these bonds, but also neutral. 2, 4, 6, 8, full octet, 1 bond, going to have that negative charge. Don't worry about the sulfur. It can expand its octet, so it's not plus or minus. It's just because it's so big, it can have more bonds. So this is HSO4. And hopefully this counts out our electrons: 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Check. Good. All right, so HSO3 minus, going to be another one. Again, let's put sulfur in the middle. 6 electrons from sulfur, 1 from hydrogen, 1 from the extra charge, and then 6 more from oxygens. Gets us to a grand total of 26 electrons we need to have. Sulfur in the middle. Put the oxygens all around it. Let's have the hydrogen off one of the oxygens. You'll rarely ever see that sulfur or something in the middle with the hydrogen bonded to it. That just usually doesn't happen. So some people might say, why not put the hydrogen on the sulfur? Usually the hydrogen ends up on the oxygen out here. Right? And if you know something about the chemistry, it's like a conjugate base again. So again, let's see. Let's start putting some lone pairs in. Sulfur, like oxygen, right? You would expect it normally to want to have a full octet and only maybe have 2 bonds, but because it's bigger, it can do some different stuff. But right now, this sulfur has 2, 4, 6 electrons around it. So one way to alleviate that would be to draw in another bond. Now, why did I choose this oxygen, not this one? Because if I chose this one, now this oxygen would have, if I give it some lone pairs, right now, is it happy? Yes, it is. It has 2, 4, 6, 8, full octet and 2 bonds. That's neutral. Why mess with something that's already happy? Whereas these single bonded ones, we can do a little more moving with electrons wise. But here, is this oxygen going to be happy? Should be. 2, 4, 6, 8, full octet, 2 bonds, neutral. Let's fill in some more electrons out here. Let's get everybody to have a full octet. The most important rule is the octet rule, so try to get everybody to have a full octet. 2, 4, 6, 8, oxygen with a full octet with only 1 bond would be an oxygen with a negative charge. Again, sulfur is weird. I showed you something with sulfur with 6 bonds that's neutral. Now I'm showing you something with sulfur with 4 bonds that's neutral. I'll also show you something with sulfur with 2 bonds that's neutral, and that's just the way sulfur goes. It's a little different. So that works out too. So be sure to look at this video, take a look at the other ones, slow it down, stop it, come with questions. We'll keep working on this.